Marcel Szakály, Eszter Varga Umrik, and Balázs Norbert Nagy. I am Tima Bános, the team of the captain of the team, and these things are our mascots. They are Hungarian police, they are dogs, and the name of them, the black one is white and the white one is black, of course. And we wish everyone a good luck and hope that everyone will enjoy this fight. Thank you.
Thank you. And we have the team from Poland, please.
Welcome, ladies and gentlemen. We are Team Poland. In our team there are Adam Grzela, Bartłomiej Lewandowski, Filip Kubacki, and Michał Kubacki. And I'm Maciej Augustynowicz, and I'm the team captain. We wish you an exciting fight.
Thank you very much. Team from China?
Well, hello everyone. We are the national team from China. I'm the team captain Liu Yiran, and here are my teammates: Wang Chunbing, Ding Ruyi, Zhu Haotian, and Liu Hanbai. We wish to have an excellent discussion with you. Thank you.
Thank you very much. And last but not least, the team from Singapore.
Good morning, everybody. Xing Hong, White, Rachel, and our team mascot, Mark the Monkey. We wish everyone a pleasant physics fight. Thank you.
Thank you very much. And now I would like to invite the jurors to introduce themselves, please.
Good morning, everyone. My name is Mattias Andersson. I'm a physics teacher from Sweden, and I hope to see a good fight today.
Thank you.
Good morning, everybody. My name is John Balcombe. I'm a physics teacher from the United Kingdom, where I've been teaching physics for 35 years. And I wish also the teams in the final to have a great fight, and I hope they all enjoy the final. Thank you very much.
Thank you.
My name is Elias Kenazi. I'm from the United States, from the University of the Sciences in Philadelphia, where I'm a physics professor. I wish everyone a great fight.
Thank you.
Good morning. My name is Hong Jung. I'm a professor at Sumyang Image University of Seoul, Korea, and I wish you good luck to every team.
Good morning, everybody. My name is Daniel Keller. I'm a teacher in Switzerland. I'm involved in IYPT since 2005. I wish you all a great fight. Good luck.
Thank you very much.
My name is Ilya Marchenko. I'm involved with the Foundation for Youth Tournaments in Moscow, and I happen to be a participant of this competition 16 years ago.
From New Zealand. I'm a physics teacher there, and I'm looking forward to a great competition.
Thank you.
Good morning. I'm Philip O'Neill, retired physics teacher from Australia, and I've been involved since 2003, and looking forward to an interesting competition. Thank you.
Thank you very much.
Good morning. My name is Tomáš Opatrný. I'm a physics professor at the Balázs University in the Czech Republic, and I'm looking forward to great physics today. Thank you.
My name is Juan. My name is Liu Kusri. I teach physics at Chiang Mai University, Thailand, and I wish every team success.
Thank you very much. My name is Martin Blesch. I'm the president of Young Physicists Tournament, and I'm also the researcher at the Slovak Academy of Sciences and Maastricht University in Bern. So I hope everyone's ready now. Reporter, opponent, reviewer, timekeepers, very important part of the stuff here. Okay, in that case, I wish also all of you a pleasant fight. And just before we start, I remind you again, we have a tight schedule, so we'll be tight with the times. And if you manage to finish your whatever presentation, opposition, reviewing, concluding speeches within the time, it would be great, because then I don't have to interrupt you. And I also have a small request to the jurors. We have a big jury, but we still kept 5 times for the jury questions. So consider the questions you would like to ask, whether they are really qualifying, clarifying questions, and whether they allow brief answers, because if you pose a big question which requests a big answer, then it's a problem to get a chance to have a joke. Thank you very much, and please, Hungary, prepare your report.
Everyone, my name is Nagy from Team Hungary, and I will present you today my results in the IYPT problem number 9, ball in the tube. So let's see. I had to take a tube and fill with a liquid. I had to put a small ball in it and attach its lower end to the motor such that the tube traces a conical surface. We had to investigate the motion of the ball as a function of the relevant parameters. So let's see how we did it. First, I want to speak about the theoretical approach of the theory of the phenomenon, about the equilibrium positions, about the buoyancy force. After that, I will show you our experimental setup and how we measure with that. After that, I will show you the dynamics of this phenomenon, and I will summarize my presentation. So let's start with the theory. We have the center of rotation, and we have the tube in a given angle. Let's get a little bit closer and investigate the buoyancy force, because that is the most important part of this phenomenon. Let's take a small volume unit of water and investigate the acting forces on it. There will be the weight, and there will be the centrifugal force. The sum of these two forces will be an effective gravity force, and if we investigate this effective gravity force in every point of the tube, we will get an air-depending effective gravity field. Okay, but we also know that this volume unit of water is in equilibrium, so we can easily determine the buoyancy force. But let's see what happens. So we can determine the buoyancy force with the uneasy Pythagorean theorem. But let's see what happens if we change this volume unit of water to a ball that has a smaller density than the water. In this case, we know from Archimedes' principle that the buoyancy force will be the same, but the effective gravity force, the magnitude of the effective gravity force will change. So we have a net force that shows the same direction than the buoyancy force. And if we have a net force, then the ball starts to move. The ball will move until it touches the wall of the tube, and there will be in equilibrium because of the normal force. So we can say that the ball is in equilibrium if the buoyancy force is perpendicular to the wall. And that means also that if the tube is in a given angle of alpha, then that angle has to be alpha 2, and the condition of the equilibrium is that equation. If we rearrange it to R, that gives, this formula defines the position of the equilibrium position from the rotational axis. Okay, let's investigate the two cases. If the density of the ball is smaller, and the density of the ball is bigger than the density of the liquid. If the density of the ball is smaller, then the ball will be on the top of the tube, and it's very important that the buoyancy force in this case is bigger than the effective gravity force. So if we diffract it, then the net force will show in that direction. On the other side, the same situation, so the equilibrium state is stable. If the ball density is bigger than the liquid density, then the effective gravity force is bigger than the buoyancy force, and if we diffract it, then the net force will show in that direction. On the other side, the same. So this equilibrium state is unstable. So let's sum up a little bit the theory. We can see that we have a frequency-dependent equilibrium position. It means that if we increase the frequency, the ball comes closer to the center of rotation. But we have to see that we have two cases. If the equilibrium state is unstable, then the ball won't be on these positions. It will be in the bottom of the tube or in the top of the tube. But if the equilibrium state is stable, then the ball will be on these positions. So first we wanted to measure out the stable equilibrium position because it's much easier. So let's see our experimental setup to this. We had the plexi tube filled with liquid, we had a small polystyrene ball in it, and we had the DC motor connected to the rotating table. We had the light barriers and 32 sticks to be able to measure the frequency, a protractor to measure the alpha, and the rotating digital camera. And what we exactly did, we investigated the position of the ball as a function of the frequency on given angles, and we measured with these geometrical parameters of the ball and with these of the tube. What we exactly did, that we started to rotate the tube and we increased the frequency. If we increase the frequency, the ball comes closer to the center of rotation, and we took pictures. We took pictures in minutes or in seconds that the ball didn't move. So we knew the frequency on this sac, and we also had a picture. With analyzing the picture, we also knew the position of the ball from the rotating axis. And here you can see my results. You can see that it's very interesting that every point is above the line or on the line. But what is the reason of it? The reason is the friction force. Because if we increase the frequency, then there will be a friction force that keeps the ball in equilibrium position, but just until it reaches its maximum. After that, if we increase more the frequency, then the ball starts to move in a new equilibrium position. So we improved our measurement method, and first we measured with low starting frequency and increased the frequency, and after that, in this case, the friction shows upwards, and after that, we started from high starting frequency and we decreased it. In this case, the friction shows shows downwards. And the results we got. You can see that by increasing, the deltas are above the line, decreasing below the line. But we wanted to know that these scatters are really because of the friction, or there is another influence maybe. So we wanted to know how big the rolling resistance coefficient in these cases, and we wanted to put in the theoretical approach we wanted to put in the friction influence in a theoretical approach. So we took the tube and we lifted the end of the tube, and we knew from easy math that if the ball started to move, that the tangent of that angle has to be equal with the friction coefficient or the rolling resistance coefficient, and we made these measurements many times, and we got an average that the rolling resistance coefficient is about 0.065. So we put static friction in our theoretical approach, and you can see that it causes an extended stability range. And you can see also that there are, so almost every point is in this gray area. After that we measured the stable equilibrium position, we wanted to measure the unstable ones, but it's not so easy, so we had to improve our experimental setup. We had to raise the height of the experimental setup to have enough space for the camera, because in this case the ball is on the bottom of on this wall of the tube, and we also had to use a steel ball because its density is bigger than the liquid density, and we also had to make a magnetic trip gear to remove the magnet and let the ball go at the required time during the rotation. And it includes an extended spring and the magnet of the end, and also a servo motor which we could rotate in a transmitter. And we made measurements with that, and you can see on these graphs that the blue dots are the cases that the move moves downwards, so it means that to the center of rotation, and the red dots that the moves upwards, so from the center of rotation. So from this, until now, we investigated velocity-independent forces. For example, the gravity force and the centrifugal force. That the sum of these is the effective gravity force, as I mentioned, the buoyancy force, which is very important, the normal force, and the static friction. But there are also some velocity-dependent forces. For example, the rolling friction, but it depends just on the direction of the velocity, and there are also the Coriolis force and the drag force. So let's see first the Coriolis force. You can see here the formula of the Coriolis force, and that we can define the direction of the Coriolis force with the right-hand rule. And you can see also that we made some simulations for that. So we made some simulation for that the Coriolis force deflects the ball from this trajectory, and we could also observe it in our measurements. So the other velocity-dependent force is the drag force. In this case, it's very important is the Reynolds number, that is dependent from the velocity. So if the velocity is small, then the Reynolds number is also small, so about or below 2,200. And in this case, the flow is linear, so we can use a linear velocity dependence. But if the velocity is high, then the Reynolds number is also high, and we can't use this linear velocity dependence, but the quadratic one. So to sum up these forces, we can say that this is the equation of the motion, and it's very important that the nature of the motion. So the nature of the motion influence. So the drag force influence mostly the nature of the motion. It means that it can influence that it will be an oscillation or there will be no oscillation. So and the drag force depends on the viscosity. But what we could see in our measurements. So we took the ball and we released from far the equilibrium point, and the ball directly approaches the stable equilibrium. You can see here the starting position, and this is the equilibrium position. We also had to coat the ball with a ferromagnet liquid to be able to stay here the ball, and during the rotation let it go. And you can see on this video that this dynamic is overdamped. So there is no oscillation because of the viscosity is too high. And to make a conclusion, you can see here the statics. First, the equilibrium position defines the angular velocity, the inclination of the tube, and the length of the tube. The ratio of the densities defines the stability of the equilibrium position, if it is stable or unstable. The coefficient of friction can define the extension of the equilibrium region. And at dynamics, the most important part is the viscosity and the mass of the ball, because these can influence the nature of the dynamics. So to summarize my presentation, first I investigated the acting forces, and in the co-rotating system, the static, but it's also motion of the ball because it's on an orbit. And after that, I also investigated in two different cases, if the ball density is smaller than the liquid density, and the case that the ball density is bigger than the liquid density. We saw that there are a stable and an unstable equilibrium position. We also made some measurements, and we also could calculate with the friction influence. And we also improved our experimental setup to be able to measure the unstable equilibrium position, which I think are really good results. And you can see here the results of the improved experimental setup too. And after that, we investigated the dynamics of the ball in the co-rotating system too. And I made also some conclusions, which I can say that there are mostly two important parts: the static in the co-rotating system and the dynamics. And I think that I also investigated both of them deeply enough. So thank you for your attention.
So now we have time for questions from the opponent, please.
How did you ensure that the rotational velocity of the tube was constant?
The rotation?
Yes.
So I measured the frequency, and then I saw that it's constant or not.
Okay. So did you use any releasing mechanism, or was this released from the starting of the rotation of the tube?
What do you mean by using some
Sorry, thank you. Have you changed the size of the ball?
No, I didn't, because that didn't influence the phenomenon.
Okay. Have you compared the dynamics theoretical model with the measurements?
The dynamics theoretical with the measurements?
Yes.
Yeah, I compared it.
Okay. Have you changed the liquids?
No, because it doesn't matter.
Okay. How have you ensured that there's no air bubble in your system?
Because I used destillated water, and there are no bubbles in this case.
Is there any terminal velocity for the ball in the system?
Terminal velocity, what do you mean by that?
By the velocity that the ball can't exceed during the motion.
Yes, there is.
Okay. And what is the Reynolds number in your measurements?
In the measurements?
Yes.
Yes, so I didn't define the Reynolds number by my measurements exactly.
Yes, but what is the value of the Reynolds number in your experimental setup?
So it depends on the velocity.
Yes. What was the maximum value of the Reynolds number?
I didn't define it exactly, just that it's
Okay,
under 2,200 or below, it doesn't matter.
Thank you. Did the ball rotate during your measurements?
The ball rotates?
Yes.
So you mean roll?
Yes.
Yeah, roll, yeah.
Okay, thank you. Is acceleration of the, what is the character of the float around the ball?
It can be also turbulent and also linear.
Okay.
It depends on the velocity, as I mentioned.
Okay. Did you observe, because I didn't understand from the presentation, did you observe underdamped oscillations of the ball?
No.
Okay. What is the
I'm sorry, the time is over. You can pose further questions in the discussion. Time for preparation is over. Please start.
Welcome, ladies and gentlemen. My name is Nagy, I represent Team Poland. Today I'm going to present you our opposition task number 9, Module 2. Firstly, the program content has several important parts. First important part of the of the problem is investigating the static theoretical predictions for the dynamics of the ball. And this part of the task was done fairly well, but there was not enough investigation of the drag force acting on the ball. Secondly, the discussion of how the parameters of the liquid affect the motion and the pressure distribution that causes the motion of the ball. And this part of that was also done very well, but there was absolutely no investigation of how the viscosity of no experimental investigation of how the viscosity affects the motion. And third important part of the task is investigating the force analysis and the motion of the ball, and discussion of relevant parameters affecting the ball motion. And there was also no investigation of no experimental investigation of the motion of the ball, and no changing of the liquid parameters in the experiments. However, the presentation had some positive aspects. Firstly, there was a quantitative theoretical prediction for the equilibrium point using the equilibrium of the forces. Secondly, there was analysis of forces acting on the system on the ball and on the liquid parameters, which defines the equilibrium point. And there was experimental analysis of the equilibrium point, along with the discussion of the measurement of this. There was also mentioning of drag and static friction. However, there was some errors in it. I will discuss it during the discussion. There were various parameters of the liquid investigated, such as angle of inclination over angular velocity of the tube, and investigated and they compared the theory for the equilibrium point with measurements, and it agreed with the theoretical model. And there was also discussion of the Coriolis force. However, I think this was insufficient because there was no mentioning of the Coriolis forces acting on the elements of the liquid, which is very important, that it might affect the drag force acting on the ball. However, there was no discussion analysis of the flow around the ball, which is one of the most important parts of the task, because the task is about motion. Motion induces the flow around the ball. The Stokes law has been used for big Reynolds number. It is applicable only for very small Reynolds number. The reporter said that this is applicable when the flow is laminar. There was insufficient investigation of viscosity. They haven't changed liquids, and they haven't investigated the drag force. We didn't know if it's linear or quadratic. It wasn't mentioned experimentally, and the wall influence can change it. Even for small Reynolds number, the drag can be quadratic. And there was lack of investigation of dynamics experimentally, and the theoretical model was not compared with the measurements, and they haven't discussed the measurement uncertainties in their measurements. Now I would like to go to the discussion. You have said there were some questions that...
Sorry, that maybe can I explain you the viscosity and drag force there, because I'm not sure that I could present it clearly enough. So maybe
okay, so yes,
should I explain that?
Sorry, you have said your questions that you have compared the theory with the measurements. Could you show me the measurements for the motion of the force of the ball?
So okay. So I mean that, for example, at the dynamics there is also a comparison, because here you have a simulation for that, and you also could see the video for that. So that is the theoretical one, and what we observed by the measurements.
Could you show me the plot?
What do you mean by that?
You are saying you have investigated the drag force using the theoretical model. Have you compared the exact drag force in your measurements agrees with the one you predicted?
Okay, but please let me explain that, okay? Okay, so I said that here if the velocity of the ball is high enough, then the ball will be turbulent, okay? Okay. But if the velocity is low, then there will be linear. And what really matters that if the velocity is not so high, then we can use the linear velocity dependence, and there is also the viscosity of the fluid there. But
formula for the Stokes law. Do you know what are the assumptions of this formula?
Sorry?
You have used the Stokes law for calculating drag around the ball. Do you know what are the assumptions of this formula?
Why don't you let me explain that? Then you really understand.
Okay, please explain.
Okay, so there is the viscosity of the fluid, and when the ball starts to move, you could see on the video that first the velocity is really high, but then if there is close to the equilibrium position, that the velocity is low enough that we can calculate with this, and there is just the viscosity matters. And do you know how big the viscosity of the water is? Really small. So we can't reach a lower viscosity, just maybe, I don't know, so if you have a boiling water that has also just yeah.
Do you know what are the assumptions of the Stokes law of putting drag around the ball?
What do you mean by that?
What are the assumptions that you need for saying that calculating the drag using the Stokes law is correct?
That if the ball is turbulent.
Sorry?
If the ball is turbulent, if you mean that.
So you are saying that if the flow is laminar, then you can always use the Stokes law, yes?
I said that if the velocity is low, then we could use the linear velocity.
Okay, so the Stokes law is applicable only when the Reynolds number is very small, and not only when the flow is laminar, but if the Reynolds number is at the order of magnitude of 1. And because they didn't also change the viscosity, the parameters of the liquid, we are not sure if the drag formula is correct. So
I can't agree with that. Sorry. So
you have said that the Stokes law is correct if the flow is laminar, and the Stokes law is correct only if the Reynolds number is close to 1. So I don't know why.
But it doesn't matter. It just influences.
This formula is not met in your experimental setup, and you haven't compared with your experiments.
But that influence is just that the nature of the dynamic is overdamped or underdamped, but we couldn't observe underdamped dynamics.
We have to investigate the motion of the ball, and the reporter said that the only thing that matters is if the motion is underdamped or overdamped. I think that we have to investigate the trajectories of the ball, including the magnitude of the drag force, and that was not investigated in the presentation and not compared to the experiments.
But
you have said during the initial questions that there is a terminal velocity in the ball. Do you agree? What does it depend on?
Do you mean that the maximum velocity of the ball?
Yes.
It depends on the drag.
So, is there any terminal velocity that the ball can exceed in your ball, in your tube?
So there is a maximum velocity because of the drag, and so it's influenced from the geometrical. So the geometrical parameters of the ball, and also the liquid, of course, because of the drag, and there is the viscosity also matters.
Okay, I think there was a misunderstanding to us. But what would happen if you change the size of the ball?
Okay, if you change the size of the ball, then the drag force will be understood because of the dependence of the radius. But if the ball is too big, then we also couldn't observe, so we can't observe the influence of the Coriolis force, for example, or you also can't.
Okay, so you are saying that that by changing the radius of the ball, the drag force increases linearly, as your theory predicts.
If we increase the radius of the ball?
Yes.
Yeah, of course. If you decrease the radius, then the drag force will also decreasing. But it's not so easy because there has to be. So we can also calculate the density of the ball, and so the ratio of the densities. So it's not so. So you can't change just one parameter.
So if you have a ball that is that radius is very close to the ball to the radius of the tube.
I'm sorry, could you switch the camera so that we see what we have? Organizers, could we switch the camera from the clock to the board? Could we pause the time?
You have a very small gap here.
Okay, stop for a moment, pause the time. Organizers, you should switch the camera so that we see the screen. That's what we tested before the fight. Okay, seemingly it's not working. Sorry for that, so please continue.
So you have a very small gap here.
Maybe go closer and then.
Yeah, it's much better. I'm sorry for that, but we agreed it was tested at the beginning, so it should have been working.
So you have a very small gap here if you increase the radius of the ball. And you are saying that the drag increases linearly, even though you can reach a very small gap between the ball and the tube. Do you think that this gap will affect the drag force in another way of linearity than the linear dependence?
Firstly, do you think that this is a small ball?
So what would happen if you increase
do you know that in the task is small ball, and I think that it's really interesting.
You can change the size of the ball, so you can say what the small ball is. for the drag dependency. You are saying that the drag dependency is linear. And
linear, but if the turbulence
is crucial for determining drag. So what would happen if you increase the size of the ball? You are saying that the dependency will be linear. Yes.
If the flow is turbulent, then quadratic. But if it's laminar, then linear.
I'm asking about the radius dependence, not the velocity dependence.
The radius dependence.
So will it be linear?
Do you see that? Yeah.
Yes, and it's okay. So what was the flow turbulent in your case?
Yeah. First, if the velocity is high, then it's turbulent. But then, if it's close to the equilibrium position, then the velocity is small, and then the laminar is the flow is laminar.
Okay. So what's the boundary velocity for the turbulent flow?
No, we didn't investigate it because it's not so. So you mean the border between the turbulent and the yeah? It's not so exactly because it's just about 2,200. But we can.
What was the value of the Reynolds number in your measurements?
We don't have to know it exactly, so we didn't determine it.
But you have investigated drag, and you are saying that the Reynolds number is not so important that you don't have to know it. Yes. So. Okay.
So what you have to know that there is a linear flow if the velocity is small, and where the equilibrium position is, there is the velocity low enough, and then what really matters is the viscosity of the clay. But you can ask them that why didn't I investigate the viscosity of the fluid? It's really easy because you can't reach a lower viscosity than the water exactly.
And then the drag will be much bigger. And
yes. And what happens? What do you think? What is the new physics when I increase the viscosity of the liquid?
So
nothing matters. Then it will be overdamped too. So nothing changes.
It's not only the overdamped or underdamped.
Yeah, the velocity will be decreasing.
It's about investigating the dynamics of the system. The dynamics of the system includes not only the thing that it's overdamped or underdamped, but determining the magnitude of the drag force and investigate it both experimentally and theoretically is important. And I think that this task was not fulfilled at all at this point. Could you please go to the slide with your theoretical, with your experimental setup?
Which one? The improved or the main?
The main.
The main, okay. You mean this one?
Yes. So on some of the photos you have shown us, the photos with a very big parallax effect. Could you please estimate the measurement error because of this?
Parallax effect?
Parallax effect.
Yeah, okay, so you mean the effect of the Coriolis force?
No, I mean the effect that your camera was pretty close to the tube and there was a curvature of the...
Yeah, of course. Okay, so as I also said that if we take photos with that, then we analyze the picture. And we calculated with that by the analyzing.
So what is the estimate? What could you estimate the parallax importance for these measurements, and how does it affect the measurement errors?
So if the ball is there in the end of the tube, then it has a larger effect. But we calculated with that, and so that has no effect in this case.
So what was the measurement error of your experiments?
It's really big, it's really small. That's the case, that is the reason that I didn't have their errors, because it's smaller than the data, than the point there.
Okay, how many measurements have you done per 1 point?
Per 1 point?
Yes.
So the 1 point is one measurement. So yeah.
Okay.
That's why I didn't have also an error.
During your summary, you have said that the static friction is independent of the direction. Do you agree with that?
The
static friction is independent.
Sorry, I said that the rolling resistance is independent from the velocity, just the direction of that, the magnitude.
And the static friction is independent of the direction.
Of the velocity, or?
Yes, yes.
The static friction, if there is static friction, there is no velocity.
Okay, but there is a kinetic friction, not only the rolling friction.
Okay.
Yeah. So is the kinetic friction.
Can you move so that I see the clock? Okay. Thank you very much. Just in time, 1 minute for wrap-up of the discussion.
The main part of this task is to investigate the dynamics of the ball inside the system. And the nature of this task allows there is a pressure distribution that makes the ball move through the ball. However, with no disruption of flow. And it's a perfect a perfect setup for investigating the drag force acting on a ball, which in the rotating system, which is still a matter of ongoing research. So I think that the main part of this task is to investigate how the drag force affects how the drag force depends on relevant parameters. And it's not sufficient to just use the standard equations for the drag because of the Wond's influence and big Reynolds numbers. So I think that investigating both experimentally and theoretically was a very important part of this task, and this was not done at all in this presentation. Thank you.
Thank you very much. Questions from the reviewer. Team China, please.
Well, thank you very much. Very inspiring discussion and report. Well, first and foremost to the reporter, and you have described the motion as only as a equation that shows the equilibrium and you prove its stability. Do you think it is adequate of the description of the motion? So you have only described the motion as a equilibrium point, and also you have proved its stability. Do you think that it is adequate to prove that this is a whole investigation of the motion?
Yeah, I think because if I'm in the static, then it's the corrotating system.
No, I don't agree at all. I think that the main part of the task is investigating force acting on the ball, and the forcing force, I mean the pressure force, is trivial. Investigating drag force.
Do you think that it's more reasonable to use a function, for example, the position and time function, to investigate its motion?
Sorry, I don't understand.
And also, do you consider to the reporter? Do you consider the rolling also as a part of the motion?
The rolling
of the ball, which means the spinning of the ball.
Yeah. So because of the friction, of course.
Of course. To the opponent, do you think that we need to quantify this rolling?
Sorry.
Do you think that we need to quantify this rolling effect, the spinning of the ball?
Yes, I think that it might affect the drag force acting on the ball.
Yeah, sure. And to the reporter, what do you think is the exact influence of the spinning of the ball to your motion?
The rolling, you mean?
Yeah.
The influence of the rolling. That because that gives a damping in the system exactly because that's a friction.
Thank you. And also, what is the applicable condition of the Stokes equation?
What is the
applicable condition for your Stokes equation?
I didn't actually.
Okay, let me go in another way. For example, what is the Reynolds number that you've been using in your experiment? Have you experimentally determined the Reynolds number?
No, as I said, I didn't determine that because yeah.
Yes, exactly. And you consider the radius of the ball and its effect. So do you think that this may have some influence on your application of your Stokes equation?
Could you repeat it, please?
Well, we're suggesting that the Stokes equation is supposed to be applied in an infinite water condition. So do you think that the ball tube, the tube will have some effect on the Stokes equation's application?
So the tube, the effect of the tube.
Yeah.
If the radius of the tube is too small, then you can't observe, for example, the effect of the Coriolis force.
Okay, to the opponent, do you think that we need to consider the effect of the tube, for example, the flow turbulence by the boundary?
What effect?
The effect of the tube on its application of the Stokes equation when calculating friction force.
Yeah, because the Stokes force is applicated only in an infinite quaternary on the fluid and for very small radius numbers.
Okay, thank you very much. And also to the reporter, and in your experiment, we have observed that in the video there are distortion. How do you calculate the distortion? For example, from the view of the camera. Distortion. Yeah.
Okay, so we calculated that with the software exactly. So we had points on the tube and we could calculate it like so that.
Thank you.
Okay, thank you very much.
Yeah. And then kind of like at this point, the three nuts are all I don't know, that might be when you put it in a tub, then you can just add either some slip or some surface like drag on the fluid, so you don't need to entire thing or something like that. Is that the case?
First, that will be my review report. And first, let's have a briefing about the question. And also, as for the report, we are suggesting that the reporter has a full perspective of the problem. He has described the motion as a function, but we are suggesting his discussion of this is actually incomplete. We are suggesting him to give out a function that shows the not just the equilibrium point, but actual position time function to describe the whole process of which before it reached its equilibrium position. And also, as for the theory part, he has given out a dynamic equilibrium and also stability of the position, and also the influence of the Coriolis force is also considered in his report. But we are suggesting that he has this the rotation of the ball, which is the rolling. This may lead to some Magnus effect, and this may have some influence on the motion of the ball. And also, as for the application of the form that he used to measure his friction, we think that it's actually incorrect and sometimes imprecise. And also in his experiment, he has found and investigated some parameters, but we are suggesting that he has lacked some parameters of the liquid as well. And these are the reviewing of the reporter. And as for the pros, he has given out the proper choice of tube and as non-inertial reference frame, and also the accurate expression of buoyancy force. But he indeed has some limitations as well. Well, he has given out an inadequate discussion of the model. Well, what will happen if the axis is not vertical? And also, in his first part, he has considered the motion to be a one-dimensional motion instead of a three-dimensional motion, with some little modification to try to make it be three-dimensional. We was suggesting that the reporter may continue this part into the first part of his report and to combine these forces into his equilibrium point calculation. And also, he has dismissed that the change of the tube rotation rate and overlook the effect of the Coriolis force as well. And also, he has an inaccurate analytical expression as a friction, and as I have just stated above. As for the opponent, we are suggesting that in the discussion, the opponent indeed have captured some problems, but he lacks a point of going deeper into the deeper physics of his problem. And also, he has also overlooked experimental details, for example, the distortion from the view of the camera as well. And we go to the part of the clashes between the opponent and the reporter. Well, as for the reporter, and he's suggesting that he has no measurement of the rotation of the ball, and the opponent has mentioned that part. But we're suggesting that this rotation of the ball must be integrated into his friction expression, because this may lead to some effect called Magnus effect, which is the rotating of the ball in a liquid. And also that in his calculation of Reynolds number, the reporter has no actual calculation of Reynolds number, and the opponent has noticed that problem. We're suggesting that he is not going deeper. We're suggesting that the reporter is actually somehow unconvincing, and the real situation is actually much more complex. We need to consider the flow turbulence that is led by the tube, and also we're suggesting that his calculation of friction force is actually not applicable under this condition. And also, the reporter has no influence to the measure of the motion, and we have actually lacked some, the opponent has raised some factor as well, for example, the viscosity of the liquid as well. And also, these are the missing points that the problem requires us to describe it as a function of motion, but we're not suggesting that the reporter has fulfilled that part of the requirement. And these are our suggestions. We're suggesting the reporter to consider different physics and also to investigate more variables and to combine them into this description of the motion. Thank you very much.
Thank you very much. So thank you for the discussion. And you mentioned the reviewer and the opponent to the flow next to the ball and the Reynolds number. But I think that in investigating this, that the motion is overdone or underdone, because I think this is the most interesting thing in this phenomenon. So that's why I investigated that. And in this case, it doesn't matter really how exactly the Reynolds number is, just that the flow is linear on there is or turbulent. So that's why I didn't calculate it exactly. And about the opponent, just also the use of the Stokes law, just I think that it's the same, that if the velocity of the ball is small enough, then we can use there, and there the viscosity matters, but I couldn't decrease the viscosity of the water because water has also a really low viscosity. And the reviewer, I hope that maybe you will some questions to equilibrium position or to the experimental setup, because I think that the opponent didn't mention that just the Stokes law and the flow around the ball. So I little bit missed that in this discussion. But and you also mentioned the one-dimensional or three-dimensional. If the ball touches the ball, then we can say that there it moves just in one-dimensional. And I'm not really sure that you challenge my theory, because I think that the main part of the theory is the explanation of the equilibrium position, and you didn't ask to them. But altogether, I want to say thank you for the discussion. I really enjoyed it. I really enjoyed that we are in the final. So thank you for your attention.
Thank you very much.
Want to observe underdamped motion? How would you modify your experiment?
So if we could reach, for example, a smaller ball, but with the same density of increasing the mass of the ball without increasing the radius of the ball, then maybe we could observe that, or with decreasing the viscosity. But yeah.
Thank you. I have a quick follow-up question. If you would just increase the diameter of your ball, so take the same material, water, same tube, just take a bigger ball, would it help with changing the character of the motion?
So bigger ball, but
bigger R.
The same mass?
No, the same density.
Same density, bigger ball, and how it influences the motion?
Could it change the character of the motion to underdamp?
So the damping would increasing. So it would be overdamped too.
Thanks.
To the reporter, you said that I saw that the animation you showed is you said that it's the result from the simulation, right?
Yeah.
And how do you put the form of the drag force in your simulation?
The drag force, you mean? So the static one in the theoretical. If we investigate in the equilibrium state, you mean the static friction?
The whole motion. The whole motion depends on the animation.
We put in that just damping influence. With differential equations, so we put it in the software. Yeah.
What kind of equation do you use?
For the friction. For the friction.
Yes.
The and the moment force. So just the most easiest way to do the friction.
Okay. See you.
Quick question to the opponent. Can you just define terminal velocity, because you asked the reporter?
So I think that the reporter said the terminal velocity is present. I think that there is no the terminal velocity changes with time, so there's actually no terminal velocity within this setup.
Okay, thank you. Daniel?
I have a question to the opponent. You said the Stokes friction is not always applicable. So how would you improve this part of the solution, the friction part, and how would you control it?
I think that calculating the drag theoretically is very hard, so I think that maybe in this setup, so I think that maybe it should be experimentally calculated, and then included into the model of the ball in a rotating setup.
Thank you, Ilya. Okay, the reporter, please. Let's take one of your experimental data points. The ball is neutrally buoyant inside the tube, and it is at a particular distance from the center. Did you observe any small oscillations around the equilibrium position, or the?
Yeah. So no, we didn't observe oscillation, but there could be, because, for example, so you mean just so we didn't observe any oscillation, but there could be maybe something. But the damping is high enough that there is no oscillation.
Thank you.
Okay.
So reporter, have you considered static friction in your simulation of the dynamics of the motion?
Sorry, I'm not really understanding.
Have you considered static friction?
Yeah.
You mentioned static friction.
Yes.
How does it affect the motion of the ball?
The motion of the ball didn't dependence on, so there is no static friction if the ball moves.
Okay, thank you. John?
question for the opponent. In the context of this investigation, how would you define small ball?
I think that there is no like one definition of the small ball, and to investigate this, we need to experimentally change the size of the ball.
Is this relative to the tube or in absolute terms?
Yes, relative to the tube, because there is ball influence, which depends on the ratio between the diameters of the ball and the tube.
Good, thank you. A quick question, very quick one, if we have one. If no, then thank you very much. And here's time allocated for grading, but we need to let the jurors to finalize the grading. Okay, it seems we are ready. Let's make a final double check of the summing rule. And if it's fine, then I will please show us the grades for the report now. It's a 7, 6, 6, 6, 5, 7, 7, 6, 6, 6, and 7. Thank you very much. Grades for the opponent. No. It's a 5, 8, 7, 7, 6, 7, 8, 7, 8, 9, and an 8. And the grades for the reviewer. No. It's a 6, 6, 7, little attention, 8, 6, 8, 7, 8, 8, 7, and a 7. Thank you very much. So can I quickly see the list? Thank you very much. Sorry, I borrowed it for a minute. There was a single 5 for the report, so this is something we need to comment a little bit, Hunk.
In my opinion, the reporter spent too little time discussing the main task of the problem, investigating the motion of the ball. You spend too much time describing the statics, the equilibrium state. So in my opinion, you fulfilled the task just by partially. That's the reason why I gave you 5. That's the average point for me.
Okay, thank you. To praise a little bit, can anyone of the 7s, Daniel, Ilya, or Nirut, make some short comment? So Daniel, you look like eager.
Basically, I partially agree with what my neighbor said. So you focused first on stability, and I think that was really done in a nice way. I was pleased by the diagram you had with the deviation, and then you gave us a regime where you said it's depending on friction. That was really cool. And the thing with the motion, I was not really sure whether you went into depth with that friction force that should be really controlled in that way.
Okay, thank you, but to obey our rules, could I both ask you also to comment on the partial grades? So how many points did you give for the report, the discussion and the questions?
Okay, so I gave you actually, for the report I gave 4 points, that's already said. And then for defending a solution, then I ended up with 2.
Okay, and Hunk?
0.5 for the report and 1.5 for the discussion.
Okay, thank you very much. Then for the opponent, we had single grades on both sides, and I was the bad guy for you today, giving you 5. So I gave you only 0.5 points for questions, because you asked a long series of questions, but it was not really used for anything later on. So you had a series of questions, and I was expecting, so okay, you are probably interested on what comes on, and then you will use it in your discussion, etc. But it looked like, honestly for me, like you have prepared a list of questions yesterday in the evening, and then just asked it without being very relevant for the discussion. So I gave you 0.5 for the questions asked, then I gave you 2.5 for the opposition speech, which I considered quite good, and filling, I was not really happy with the prioritization form. And for the discussion, I gave you 1.5 because I was lacking a clear aim of the discussion. So you were discussing interesting stuff, but there was no clear outcome. So what is the aim to show within the discussion? So this ended up in 5.5, and then I decided to round it down to 5. But yeah, there was so much who was much more happier about the opponent, so it was a 9.
Okay, thank you. From this side, optics is probably a different. My partial grades, the arithmetic was 1 plus 1.5 plus 3 plus 3.5, and from my point of view, this was one of the best oppositions I have seen, because basically all the questions which I wanted to ask were asked here, or the objections I would like to raise were raised here. So basically, this is what I more or less expected.
Okay, thank you very much. And for the review, we had on one side 3 times a 6, on the other side 4 times an 8. So unless anyone wants to comment, I don't have to ask. Okay, if not, then yeah, once again, thank you very much for your performances, for your ratings. And as I mentioned before, we are a bit under